last part. So today I want to show you a few experiments that have been done with these artificial gauge fields, and how I want to show you a few experiments to tell you how we can measure the geometric properties and the Chern number of the band that we have engineered by these artificial magnetic fields. So just to recap, basically what we ended up doing last time is to discuss how an artificial magnetic field can be engineered with periodic driving. So we had this two-dimensional lattice where tunneling is inhibited along X, and there's just bare hopping along Y. And then we apply this periodic modulation that is resonant with the energy difference delta between neighboring sites in order to imprint these phases onto our tunnel couplings. And then we interpret the finite phase that we pick up around a closed loop, which is just the sum of these two bonds, and interpret this as an artificial magnetic field. Now, with this scheme, we can realize the so-called Hofstadter model, or Harper-Hofstadter model, where we have this gauge field piercing one unit cell of the square lattice, and it's uniform across the square lattice. And then the properties of this model just depend on phi per plaquette. So if you compute the single particle energy spectrum, the only parameter that governs the spectral properties of the system is the flux per plaquette. Now, if you want to solve this problem, it's a little bit similar to what we have discussed for the two-side SSH model. That is, we have to first find what's the translational symmetry of this model. So we saw in the SSH model that we get two sides per unit cell, these A and B sides. But also in this model, although the magnetic field is uniform, the unit cell is larger. It does not contain only one side. It's not the translational symmetry of the lattice anymore. We have to respect the symmetry of the vector potential that we apply as well. And the new symmetries are the so-called magnetic translation symmetries. And I will not go through the details of the calculation because I want to show you more experiments. But in essence, what you can show is that the magnetic unit cell always contains an integer multiple of 2 pi. So in this example of a magnetic flux of pi over 2, the magnetic unit cell would be 4 times larger as compared to the usual unit cell of the lattice. Which also means that if we solve this problem, we essentially have 4 non-equivalent sides per unit cell. Which means if you go through the diagonalization, you will find that instead of having one lowest type binding band, it splits into 4 magnetic mini bands. And then you can play this game further. So you can make a flux of 1 over 3, let's say, and then you get a magnetic unit cell that is 3 times as large, 1 over 5 would be 5 times as large, and so on. So if you go through this calculation and plot the energy spectrum, or the energy as a function of the magnetic flux per unit cell, so here that's the typical unit, the flux per unit cell divided by the magnetic flux quantum. So in our case, that would be 1 over 4. So it's basically the phase divided by 2 pi. Then you see that this is the lowest tight binding band. There's no flux, so it goes from minus 4j to plus 4j for a two-dimensional lattice. And then if you pick certain ratios, then you find these mini bands. So for 1 over 4, you would find the lowest band, 2 bands that touch at the middle, and then a higher band. And the same if you go to other ratios. Here, 1/2, they're actually 2 bands, and they touch at Dirac points at the center of the spectrum. So this is how you get to this very nice Hofstadter butterfly, which has the self-similar structure that you may have seen already. Now, the lowest band in this particular example of 1 over 4, which is the one that has been used most often, the lowest band has a Chern number that is equal to 1. So the topology is equivalent to a Landau level. And if we take the analogy to the continuous limit, we could hope to engineer fractional quantum Hall states in this band. So basically, we are interested in studying interacting phases in this lowest band. So we want to include interactions between the particles. And that's actually a very hard problem. It's very difficult even to compute or find out if the Laughlin phase is stable in this lattice geometry. So let me just take one step back. So the Landau level limit is actually down here. So if you would look normally at a solid where you apply a magnetic field and you get the Landau levels, then this is the limit down here. Now, if we go to larger and larger magnetic fields, then at some point, the characteristic size of the cyclotron orbit, given by the magnetic length scale, will become smaller and smaller. So at some point, you reach a field that is strong enough such that there's a competition between the magnetic length scale and the lattice constant in your system. So this is also the limit where the dispersion of the lattice starts to play a role. So even if we know that fractional quantum Hall states are stable down here in the Landau level limit, in the continuum limit, it's not immediately clear that they will also be stable up here if we have these strong magnetic fields where the dispersion of the lattice matters. Nonetheless, so what one tries to do, because we want to study interacting physics, is to maximize this ratio of the gap between the lowest band and the next higher lying band with respect to the bandwidth of the lowest band. And the reason is that we want to have a flat band, which is more similar to a Landau level. So we want to have a small bandwidth and a large gap so that we can play with interactions without coupling to higher bands. And for 1/4, this ratio is actually quite nice. And it's very close to, I think, the optimal gap that one can get for a Loveland phase, for example. Okay, so let me show you one additional idea in order to tell you how we can generalize these ideas. So I've shown you that we can engineer these artificial magnetic fields and we can see cyclotron orbits. But maybe you want to do more, right? Maybe you're not happy with that alone and you want to study quantum spin Hall systems as well. And I will not go into the details what quantum spin Hall systems are, but I just want to tell you what the simplest example of that would be. It's a little bit trivial, but the simplest example would be 2 copies of a quantum Hall system, where now the field is spin dependent. So spin up sees a field pointing up and spin down sees a field pointing down. And in the system, then the spin down particles would see a Chern number of -1, spin up particles would see a Chern number of +1. So we get these edge currents which circulate in opposite directions for the 2 spins. Now, of course, you can make that more complicated and couple the spins, but maybe let me just show you how you can realize such a system, which is just a trivial copy of 2 quantum Hall systems. So this is one example. So we play with 2 internal states, spin up and spin down. This is again for rubidium atoms. So we can choose 2 Zeeman states which have opposite magnetic moments. So now if we go to the scheme that I've explained to you yesterday evening, and we create this linear potential by applying a magnetic field gradient, then what happens is that spin up will see an increasing field gradient and spin down will see a decreasing linear potential. So now if we apply the exact same scheme, so we shine in our additional laser beams, apply this shaking technique, we imprint our phases, then we get to the sign change in the direction of the effective magnetic field. This was due to the properties of the Bessel function that I've shown you yesterday. So if we flip the sign of the potential energy difference delta from +1 to -1, then we also flip the sign of the phase that we imprint on the tunnel coupling. So by using the exact same lattice setup, just playing with the internal degrees of freedom of the atom, you can engineer a field that points in opposite directions. And the first toy example or toy measurement that you could do is again looking at the cyclotron orbits. So what do you expect that then, depending on the internal state of the atom, the circulation of the cyclotron orbit would vary. So one goes clockwise and the other one goes anti-clockwise. And this is exactly what you see. So 0 time is in dark, and then as time progresses, it becomes lighter. So you have a spin up that circles like this, and you have a spin down that circles in the opposite direction. And that's exactly what you would expect. Now, I think this you have seen already in Jacobo's talk, maybe, but this idea of periodic driving on Floquet engineering is very general. You can apply it essentially to any system. It doesn't have to be an atomic system, but you can play with superconducting qubits or coupled photonic waveguide arrays. So here's one example that has been realized. It's basically 3 coupled sites, and then the coupling in between the 2 sites is varied periodically in time. So here in this example, it's the tunnel coupling. But if you go through the formalism, you also find that you engineer these complex hopping matrix elements, similar to modulating the potential energy difference as we have done in our experiment. And then one of the first realizations was really in coupled waveguide arrays, where you know that now this periodic time modulation is what's the propagation direction into the plane. So the z direction is time, So here that you see that this shaking of the hexagonal lattice implemented with coupled waveguide arrays. And now these ideas are more and more applied also to real solid-state systems, as graphene, for example, where you can also apply this periodic shaking by shining in circularly polarized light and to open up a gap at the Dirac cones. So I will tell you a little bit more about opening up a gap at the Dirac cones for graphene lattices in order to induce non-trivial properties in solid state. Now the energy scales are actually very different for solid state realizations. So it's very far from the high frequency limit. So typically there's a stronger coupling between the frequency of the light that you apply and the bands. And then there are these synthetic dimensions, which I very briefly mentioned yesterday, where now you have a lattice along x, and you replace the perpendicular direction by an internal degree of freedom by Zeeman states, for example. So this lag perpendicular to the lattice axis then depends on the species that you're working with. So for instance, if you would work with rubidium in the ground state, then you get 3 lags because you have MF -1, 0 and +1 in the lowest hyperfine manifold. But you could play with different atoms. You could choose one which has F = 3, for example, and then you get more internal states. And that's also why with dysprosium it was possible to have such a large synthetic dimension perpendicular to this real space lattice axis. And that's of course nice because something that is not so easy to do in our cold atom systems is to have a very nice homogeneous flat lattice and then sharp edges by applying a box. And you may want to do that just to study edge physics and just to see the propagation of edge modes and study these physics in more detail. Now in synthetic dimensions that's very easy to do because you have a very sharp edge. So you just start at MF -1 and there's no way to go in this direction because there are no available Zeeman states. And then just to very briefly mention how these phases are imprinted, essentially it works in a very similar way as the shaking. So you could interpret even our shaking protocol as a 2-photon Raman transition if you want. And that's what is applied here. So in order to couple the synthetic dimensions, because if you were just to work with atoms into -1, they stay there and nothing happens. They will just move along the lattice axis. But now to couple the synthetic dimension, you use 2-photon Raman transitions, which are detuned with respect to a higher lying state. So you have omega-1, omega-2, and delta. So your 2-photon Rabi coupling is proportional to this. But it's a complex number. And the phase factor that you have here depends on the phase of your Raman beams. Or for this 2-photon process, it depends on the wave vector difference between the 2 Raman beams. And that's essentially exactly the same as what I've shown you yesterday in this periodic driving scheme, where we also have 2 beams. And you can interpret this as a 2-photon process. And then again, you end up having this wave vector difference in the exponent of the coupling. So it's essentially the same idea, which also means that this phase that you imprint is again purely given by the geometry that you choose. So if you change the orientation of your Raman beams with respect to the lattice axis, you can engineer any phase that you want. And this is what is shown here. So this is a picture that I've taken, I think, from the Spielmann paper. There were 2 papers more or less at the same time from the Falani group and the Spielmann group, where you see this was implemented with the terbium atoms. Here between -5½ -1½ and +3½ you have one real dimension and the synthetic dimension, and then you imprint these phases along the synthetic dimension, which is given by the 2-photon Raman coupling. And here's again this nice realization from the Paris group, Sylvain Nassemben at ENS, well, au Collège de France. Okay, so let me say a bit about, well, do you have questions about that? Sorry. Okay. So let me tell you a little bit about topology in hexagonal lattices, which you have seen a couple of times on the slides, because by circular shaking, we can open up a gap and make the bands topological. Now, just a reminder about the basic properties of hexagonal lattices. So this is a picture or schematic drawing of a hexagonal lattice, where these are the primary lattice vectors. So you actually also have 2 sides within one unit cell, which are here shown as white and black. So that's our A, B sublattices. And actually, you can apply the exact same formalism that we have seen for the SSH model to the hexagonal lattice, and you also end up with this 2x2 matrix, or this two-dimensional eigenvalue problem that you can solve. So again, all of these properties can be understood by thinking about a two-level system on a sphere. So the Brillouin zone looks like this. We have special points, high symmetry points. So there's a gamma point at q = 0. That's the lowest energy eigenstate in the dispersion relation. And we have k and k prime points at the edges of the Brillouin zone. And there's actually another high symmetry point here, which is called M, which is not so important. But that's how the Brillouin zone looks like in reciprocal space. And this is the dispersion relation. So these k and k prime points are actually here. So these are here, 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 and here, and here. And the dispersion around the k and k prime points is linear. So these are so-called Dirac points. So in the hexagonal lattice, we get two bands which touch at the edges of the Brillouin zone at the Dirac points. And if you compute the Berry curvature, it looks like this. So this is again the definition of the Berry curvature. You find that it has a non-trivial geometry, meaning that there's Berry flux or Berry curvature concentrated at the position of the Dirac cones. And this Berry curvature has a different sign depending on if you look at the k or k prime point. And moreover, if you calculate the Berry phase around such a Dirac cone, or the Berry flux associated with one of these Dirac cones, you find it is equal to pi. And depending on if you look at the k or k prime point, it is equal to plus or minus pi. And measuring this pi Berry flux that is associated with the Dirac cone was one of the first experiments that has been performed with cold atoms in order to probe the geometry, the geometric properties of the band structure in the hexagonal lattice. Now, we can try to make these bands topological. So remember, if we want to engineer bands with non-zero Chern number, we want to work with gapped bands. So we want to actually open a gap at the Dirac points so that we can then probe the properties of the lowest band only. And this can be done by breaking the time reversal symmetry, which for the hexagonal lattice can be done by circular shaking. So this you have seen by with the coupled waveguide arrays, where really what you do is you modulate each lattice side circularly in time. So for our experiments, that means you generate an optical lattice that has the hexagonal shape, and then you really move it in space. So you really do a circular shaking by modulating the phases of the lattice beams. And by doing that and going through the Floquet formalism, you will find that this opens up a gap at the Dirac cones. And this has been implemented in Tillmann-Esslinger's group. So it's a little bit more complicated lattice scheme. I will not explain that in detail, but you see that there are these piezos that are mounted to the mirrors in order to modulate the position of the lattice. And then again, this picture from Michael Rechtsmann in photonic systems, where it's much easier to see, so you really just wiggle around the lattice positions. Now this allows you to implement the Haldane model, which is a famous topological condensed matter model Hamiltonian, where now, due to this shaking that you apply, you actually also imprint complex hoppings, but between next nearest neighbors. So there's a first term, which is just our nearest neighbor coupling with Tij, so that's a real quantity. And then we have complex next nearest neighbor hopping and a potential energy difference between A and B sublattices. Now, this is, in a sense, different compared to the model that we have seen before, the Hofstadter model, because in this case, if you now look at what's the effective flux that is induced within the hexagon, you see that if you go around the complete unit cell, there's actually no flux. So you just have here your real hopping matrix elements. There's no flux within the unit cell. But if you look at small triangles, for example, where you have one connection of the next nearest neighbor hopping, there is flux. So you have the staggered flux within the unit cell, which gives rise to non-trivial properties, but there's no net unit flux piercing the unit cell. As a consequence, this also means that we don't get the splitting into these magnetic mini-bands as we have in the Hofstadter model. Instead, we always have this two-band realization in the hexagonal lattice, and then we open up gaps and we can make the bands topological or not, but we always are in this two-band Hamiltonian, or this two-band model. Okay, so a little bit of background. These Dirac cones, or this band touching at the Dirac cones, are protected by the symmetries of the model, so by time reversal symmetry. So now if we apply this phase, it opens up a gap, but it's also protected by inversion symmetry, which is broken if we apply a sublattice energy offset between A and B sides. But how this acts on the topological properties of the bands is different. And this is basically what you see in the phase diagram of the Haldane model. Okay, so this is a picture that I took from the ETH group. I don't remember which PhD thesis, but it's from Tilman Esslinger's group. So here you see the two bands. The lattice topology is slightly different compared to a hexagonal lattice. So it's called a brick wall lattice, but for the topology, it doesn't matter. And the band structure that you get is shown here. So you have two bands, and you have Dirac cones where the two bands touch. Now, ideally, they touch here. That's just due to numerical artifacts that you don't see it as nicely. And we have inversion symmetry and time reversal symmetry. Now, if you apply the complex next nearest neighbor hopping using the circular shaking, you see that it opens up a gap. And moreover, so this is not shown here, but then the Berry curvature around these k and k prime points, they have the same sign. So actually the sign of one of these Berry curvatures flips. And if you then integrate the Berry curvature for the whole band, you find that there's a Chern number non-equal to 0. So it's Chern number plus or minus 1, depending on the direction of the circular shaking, the chirality of the shaking that you apply. Now, if you instead also apply an energy offset, so you make one of these A sides, or you make the sublattice A deeper, let's say, then you also open up a gap, but you don't induce non-trivial topological properties. So this is so this is the phase diagram of the Haldane model. On the horizontal axis, you see the phase of the next nearest neighbor hopping, and on the vertical axis, you see the sublattice energy offset delta AB. So in the center is the symmetric hexagon without any complex hoppings, where the two bands touch. Okay, so that's the center point here. Now, if we move along this line, it means we open up a gap by applying the sublattice energy offset delta AB. It opens up a gap, but the Chern number of the band is still 0. If you go along this line, you apply the circular shaking, you apply complex next nearest neighbor hopping, it also opens up a gap. And now you find that the Chern number of the lowest band is either plus or minus 1, and then the excited band has the opposite Chern number. And so this is something I didn't show, but in the Hofstadter model, this is a little bit different. So we can engineer bands with Chern numbers plus or minus 1, but we can also engineer bands that have Chern number of 2, for example. So there's no reason that we are restricted to a Chern number of 1. Okay, so how can we now probe the topology and geometry of the bands that we have engineered? So there's a long list, so I should also put dots down here, so there's more. Yeah?
I guess 2 images ago, why did the Berry curvature change sign? Is there some intuitive reason?
Well, I can tell you what happens. I'm not sure it's very intuitive. Well, let me go back to this picture. So essentially what happens is here you have positive Berry curvature and negative Berry curvature. Now, if you first just make it gapped, so you open, no, I lost you again. Yeah, sorry. If you open up a gap, then what happens is that first of all, this broadens the Berry curvature, but the sign remains the same. So you just, you just open up a gap, but you don't change the topological properties of the bands. And then if you were to go along this line so let's say this is our Haldane phase diagram. This is delta. So we move first up here, and then we move down here. So what happens that if you move down here, I told you that the topology of the band can only change by a gap closing point. And what happens if you move down here is that the gap closes at one of the Dirac points. And at this point where it closes, so let's say the energy gap closes for the k prime point, then the sign of this Berry curvature flips. And it's this band touching points that are really the sources of new Berry flux or new topological properties or topological charges. And that's why you get this sign flip. But now I'm not sure that's super intuitive, but that's what happens if you calculate it. Okay. Other questions? Okay, so let's see how we can actually probe that. And you will see that the scheme is very similar to what you have already seen for the suck phase. So now the goal is to measure this pi Berry flux around a Dirac cone. So I picked 2 examples. I will first, well, actually I picked 3 examples. Let's see if I manage. The first one is an interferometry sequence similar to what you saw for the suck phase measurement. Then there's a second one that was advertised a couple of times, so I will explain you the Hall deflection measurement as well. And then there's a third one that I want to briefly mention, which allows you to map out the local Berry curvature in the Brillouin zone. That's a measurement that was done in Hamburg in Christoph Weitenberg's team. Okay, so we want to build an interferometer that allows us to probe this pi Berry flux around the Dirac cone. Now, similar to what we have seen yesterday, what we want is to vary Q. So again, we apply a force to our atom that lets us vary the quasi-momentum in time. And if this force is small enough, then we don't get excitations to higher bands, but we probe the band we are in adiabatically. Now there's a second technique how one can do that, that is by accelerating the lattice. If we accelerate the lattice by playing with the frequencies, so I should first say that the hexagonal lattice is generated by interfering 3 lattice beams under an angle of 120 degrees. We can accelerate the lattice by detuning the frequency, so then the lattice will start to move. And this applies, or if we change the frequency linearly, we get a constant acceleration. So in the reference frame that is co-moving with the lattice, it's equivalent to applying a force to our wave packet. So we always deal in this reference frame that is co-moving with the lattice. And then essentially we also induce Bloch oscillations again. So in the lab frame, we really move the lattice, we drag it across the cloud. So in quasi-momentum space, or in reciprocal space, the cloud starts at Q equal to 0, and then we essentially drag the Brillouin zone across. So the wave packet stays, but we drag the Brillouin zone across. So in this picture here, you basically start at the lowest band with your wave packet, and then you just explore your band structure, you move along. And also something I want to mention right now, because I may forget. There's another interferometry technique that I will show you later, where we actually apply a large force in order to split the cloud between the 2 bands. So you can play with the strength of your force. You can either apply it such that you move adiabatically in the lowest band, or you increase it, and then you can move up to the second band and use this avoided crossing as a beam splitter. So this allows you to do interferometry between 2 bands. Okay, it's already here now. Okay, fine. So this is what we use to probe the gap between the 2 bands. So the idea is as follows. You start again with your wave packet in the lower band. You apply the force, as I just mentioned. And now if you make it large enough, you can use this avoided crossing as a beam splitter. So you move non-adiabatically across this avoided crossing. Now you have a fraction of the atoms in the second band and a fraction in the lowest band. And then you move to a certain point, capital Q, where you introduce a hold time. Now at this point, you have a coherent superposition of the wave packet in the upper and the lower band, and the time evolution will be given by the energy difference between the 2 bands. It's just by the gap. And then you reverse the sequence, so you close your interferometer. By reversing the direction of the force, you move back. You mix the states or the fractions again by going through this avoided crossing. And then you read out as a function of time how many atoms end up in the lowest band. And then this will oscillate at a frequency which is given by delta E, or the gap at this specific point. So you could imagine that you want to probe the whole band structure of the model. You just vary this final position of the quasi-momentum where you want to measure the gap. And so by doing many of these measurements and fitting the frequency of these oscillations, you can get a map of the dispersion relation in the hexagonal lattice. So this is a measurement that was taken for 2 different lattice depths, 0.80 recoil and 2.5, where we start at the gamma point at Q equal to 0, and then we probe the gap along this path. So that's the high symmetry path. So this is the M point, the gamma point, and then we vary this final position, and this is what you see here. So here's the K point, the Dirac point where the gaps close, where the bands touch. And here you see that it nicely follows an ab initio calculation of the band structure of the hexagonal lattice. You see that there's a gap closing point at K, and you can nicely fit the dispersion, or see that for this particular lattice depth, it matches the calculations. So this is actually a very powerful tool, which we can also apply to Floquet bands. So we can also use this technique in order to measure and probe the Floquet band structure that we have engineered with this periodic driving technique. Yeah?
Is there an issue with measuring right at K because
Yeah.
you need to hold them very long to do that?
Yeah, so the oscillations become very slow, and so you also have some dephasing happening during the measurement, and then it becomes much more difficult. Okay. So this is to show you that we can probe the energy bands. Now, if we want to probe the pi-Berry flux, we reduce the strength of the force. Now we probe the band adiabatically. We only stay in the lowest band of the system. And now, this I've explained you already, so I don't think I need to go through it. But the analogy of this measurement in momentum space is really the analogy of the Aharonov-Bohm experiment. So in real space, you have this electron wave packet that travels around this region of magnetic flux. So it picks up an Aharonov-Bohm phase, which is related to the magnetic field, or the flux piercing the area of your interferometer. And exactly the same in momentum space. Now, if we circle around a region of non-zero Berry curvature, we can measure the associated pi-Berry flux, or Berry flux. And for the Dirac cone, it's equal to pi. But you could do that for any other band structure as well. So you could also decide, it would be a bit tedious, but you could decide to map out your whole Berry curvature by making little interferometers and mapping out the Berry flux everywhere. And this is the sequence. So remember the suck phase sequence that I've explained you yesterday. Again, we want to open up some interferometer. So we need to split our wave packet into two parts. So again, we apply a pi/2 microwave pulse in order to generate a coherent superposition between spin up and spin down states. And then we apply a magnetic field gradient in order to make them travel along opposite directions. Now the magnetic field gradient will be applied along the x-axis, so they will move like this. But in addition, we also want them to move up because we want to encircle the Dirac cone. So we combine this with the lattice acceleration, which is independent of the spin. So now we have two forces, one that is spin-dependent like this, and one that is spin-dependent like this and spin-independent perpendicular to that. So this opens up the interferometer. And now, similar to the suck phase sequence, we now apply a spin echo. First of all, to get rid of the dynamical phase that we have just because we have different Zeeman states. And because we want to close the interferometer again. So now if we apply the spin echo here, so we flip the spin, they will start to move towards each other again. And the lattice acceleration is spin independent. So this, if we do that in halfway through the sequence, we will be able to close the interferometer again. So they will meet at a point up here. So at this point, they are again in the same spatial and quasi-momentum mode. So we can read out the relative phase after the interferometer using a Ramsey sequence. So we apply another pi/2 pulse to mix the states and vary the phase of this final pi/2 pulse in order to read out the relative phase. And this is what you find if you perform such a measurement. So let me briefly walk you through. So there are many graphs and dots. So this is the gamma point. This is the starting point of the interferometer. So that's the center. And now you can vary the final point where you close the interferometer. So you change the area of the interferometer as you go along this line. Okay, so you move along this line. There's no phase that you pick up, no phase that you pick up, until you hit the point where you start to encircle the Dirac point. So at this point, the phase that you read out jumps to pi. And now you can make the sequence longer and longer, until you even encircle the second Dirac point at K prime. So then you change the phase again by 0 because you have positive and negative Berry flux. So at this point, the phase drops to 0 again. And this is just a mirror sequence of that by performing the interferometry sequence in the opposite direction, where you see the exact same phenomenon happening. And there's these inserts that you see here are the Ramsey measurements. So there are always imperfections in experiments. So there's always a reference fringe where you open the interferometer, you don't apply the spin echo, you just go back. And this is the black curve. And then the difference between the black and the blue gives you the relative phase that you read out in this interferometry sequence. So for the pi jump, you see that these two curves are nicely out of phase. Yeah?
Is there a reason for the shift between the blue and the black curves on the main graph?
Yes. So, of course, what I told you is highly simplified. The ideal curve would be the black solid line. And basically what we did is describe everything in in a semi-classical picture. But what we have is a wave packet in quasi-momentum space. So it has a certain extent in the q direction. And we only discussed what happens for the mean value of q. But due to the finite width of the cloud, it actually matters like where you close your interferometer. So you could think about if this is the Dirac cone. Now, if you are just about to enclose the Dirac cone, some of the atoms will have traveled around it, and some of the atoms will have have not seen the Dirac cone. And that's why you get this shift, and also a little bit of the smoothening that you see in the curve.
But then, did you not expect to have some kind of broadening of the shifting to the other one instead of just shifting on left and right?
That's true. So they applied a clever trick in order to read out what fraction of the atoms moved beyond the Dirac cone and what fraction did not, using band mapping techniques and so on. So they could achieve a high resolution, although we have this large width of the cloud. Okay. So Hall deflection, as was advertised a couple of times. And the nice thing about this measurement, I think, is that we were able to see the Hall deflection, not only with charge-neutral atoms, but it was even charge-neutral bosonic atoms. So it's really very far from the original Hall experiment that you may have in mind, where you have electrons moving in a Hall bar, you apply a current, you measure the transverse voltage. So it's really a system that is very different from what we would do in solid state. So we work at pi over 2, or this flux 1 over 4, where we have these 4 mini bands. And then what we want to do is probe the Hall deflection in the lowest band here, which has a Chern number equal to 1. And the interpretation of this transverse Hall voltage for one such band would be that it's proportional to the Chern number of the band. So in our case, proportional to the Chern number equal to 1. And so here's a picture of the band structure, how it looks like. These are the 4 mini bands, just for you to see it once. So the lowest band is relatively flat. As you can see, it has a Chern number equal to 1. Then there are these 2 bands in the middle that touch, also at Dirac cones, around e equal to 0. And the higher lying band, which again has a Chern number equal to 1. Now, here you can also see something that we have discussed before. The sum of all these Chern numbers vanishes. It's equal to 0. There's a symmetry, particle-hole symmetry, around e equal to 0. So the Chern number of the lowest band is equal to the Chern number of the upper band. OK, so what's the idea behind this measurement? Again, same idea. We apply a force in order to vary the quasi-momentum linearly in time. And then we look at semi-classical dynamics. So again, we look at the mean quasi-momentum and the mean position of the wave packet. So let's, for now, just assume we have a single wave packet. We prepare BC at a certain quasi-momentum in the Brillouin zone. So what happens if we apply a force is Bloch oscillations, as we have seen. So that's just a different way of writing it down. So the wave packet, the band, the velocity of the wave packet in the direction of the force, the band velocity, is given by the derivative of the dispersion relation of the band. And yeah, mu is here the band index. But now, due to the non-trivial geometric properties of the band, there's a second contribution to this velocity, which is transverse to the direction of the force. So there's another component of the velocity, which is proportional to the Berry curvature and proportional to the force. So we expect that if we apply a force to our wave packet and it explores a region of non-zero Berry curvature, it will start to move to the side. Okay, so if we apply the force in this direction, it will start to move perpendicular to that. Now, what we don't want to do is probe this band velocity. And actually, if we fill the complete band, due to the symmetry of the dispersion relation, this contribution simply drops. if we apply a force to our cloud and there's no dissipation, it will not move in the direction of the force. There may be some oscillation, some breathing of the cloud, but it will not move in the direction of the force. And moreover, in order to measure the Hall deflection for the complete band, we want to populate all the quasi-momentum states at the same time. So this is what is shown here. Schematically, we have two bands, and we want to populate all the quasi-momentum such that if we apply the semi-classical description, the center of mass motion of the cloud that we get for all these little wave packets, if you want, is just the integral over the formula that you have seen before. So in the direction of the force, the band velocity cancels out, but then transverse to it, okay, so just how to realize this. We have done it with bosons, and you may ask, how do we fill the whole band? Because usually we create a Bose-Einstein condensate, there are no interactions, we have just basically zero interactions, there are a little bit of interactions. And basically what we did is, well, not deliberately, but you see that the band is very flat, so very easily you work at temperatures that are large compared to the bandwidth of the lowest band. So essentially the temperature of our system is somewhere in between the two bands. So we have a temperature that is large compared to the bandwidth, but small compared to the next higher lying band. So with that you get a statistical mixture or a statistical occupation, which is on average homogeneous of all the quasi-momentum states. And for fermions, you could do a similar experiment by just having a Fermi energy within the spectral gap. Okay, so now we average over all the quasi-momenta and compute the center of mass deflection of the cloud. Now, since this anomalous velocity that we see here is proportional to the Berry curvature, and we integrate over all quasi-momenta in the Brillouin zone, we integrate over the full manifold, which gives us the definition of the Chern number. So in the end, if we compute the center of mass deflection of the cloud, it's proportional to the Chern number of the band where we have prepared the atoms in. And then it's also proportional to the force, and A here is the lattice constant of the 2D square lattice. So what we expect is that we start with our atomic cloud. We trap it in the lattice, we apply a force, and we just take in situ snapshots of the cloud. As a function of time, we will see that the center of mass just travels to the left linearly as a function of time, and then from the slope we can read off the Chern number of the band. And this is how it looks. Well, I anticipated it's linear, so this is basically what you see for short times. Here it's plotted as a function of the Bloch oscillation time, which is the characteristic time scale in the direction of the force. And you see this differential shift and how it increases as a function of time. Now, this is one example image on where we evaluate this differential shift, which means in order to get rid of systematic effects, we perform two measurements. So this, if you would just take a snapshot of your cloud, this is very sensitive to any drifts of your experiment. So if you just take in situ snapshots, it will move. So what we do is we take a snapshot for plus phi and minus phi. We just reverse the direction of the force, which means the cloud moves in the opposite direction. And then we evaluate the difference between the two. And this is very nice because even for like very broad Gaussians, you see here that the differential deflection is very small. It's on the order of a lattice constant. So that's really, in our case, it was 380 nanometer or so. So this is a very tiny shift, and your in situ cloud is very broad. But now if you have this tiny shift and you subtract two Gaussians, you can actually produce this very large signal in the difference image, which allows you to evaluate the differential shift. And this is what you see here as a function of time. The slope would be ideally exactly given by the Chern number of the lowest band. In our case, the slope is slightly reduced because the fraction that ends up in the lowest band is around 60 to 70%. And the rest of the atoms also occupies the higher lying band, which has a Chern number of -2. So they would go in the opposite direction. So you get a net displacement which is a little bit smaller, as you would expect. And so this is an alternative explanation of a Hall deflection, I would say, but it's essentially, I think, an atomic version of the quantum Hall effect. So you have a sample that probes the lowest band, and you get the deflection proportional to the Chern number. It's not a Hall insulator. It's not a quantum Hall insulator. We really just used semi-classical description in order to see the displacement, which means just integrating the Berry curvature. In order to get a real insulator, we would need to prepare a Mott insulator or insulator with fermions or something. This is not what we did. It's in principle something that you could do, but it's a Hall deflection that you see with charge-neutral bosons. Yeah.
Maybe it's a stupid question I already told it, but I don't get why the Chern number is proportional to this slope now. So maybe I forgot the relation.
Maybe you missed this one. So this is the center of mass motion, which comes from this anomalous velocity that is transversed to the cloud. We integrate over that and compute the center of mass. And then you see this is the equation of motion, which is just linear in time. And then the slope, of course, also has the force and lattice constant and so on, but this is something that we know what it is. Other questions? Yeah.
Yeah, an experimental one is, so here it's in the Hofstadter model, right?
Yeah.
So meaning you have the main field to produce the non-topological band. And so the force is produced, you also put another main field gradient in the other direction, or
Yeah, so I skipped all of this under the rug. Yeah, that's true. But so actually the Hofstadter model is not realized the way I told you it is. It's purely optical. So this is the same. We have a normal lattice in one direction, but in the perpendicular direction we have a lattice like that. And this is our energy offset delta, so it's staggered, which means if we were to just apply the beams as we had before, this leads to a staggered flux because we have the sign change basically of this energy offset. If you go from this side to this side, it has a different sign as if you go from this side to this side. And in order to rectify that, we have two pairs of beams. So the scheme is a little bit more complicated. Actually, to induce a laser-assisted tunneling only on every other bond, we retro-reflect this beam. And then we double this pair and address this bond individually in order to correct for the sign of the flux. And then in order to apply a force, you can play with magnetic field gradients again, because everything else is done optically, so you don't have to worry about
the good thing is also
crosstalk.
if you wish to use flashback or so in this situation, then you have the main field that is free.
Yeah. There are many reasons why it's not good to use a magnetic field gradient, I think, to do this laser-assisted tunneling technique. It has a lot of complications and if you try to actually do it. Also because, like one obvious one maybe is that if you have this tilted lattice, then there can be resonances. There can be a resonance between this band and a higher lying band here. So this makes everything very complicated, and you don't have that here at all. Other questions? Okay, so then the last example is from the Hamburg team, where they produced this nice map, local map of the Berry curvature in the Brillouin zone. And I briefly want to sketch the idea. Now, this is again in a hexagonal lattice. So they generate it in the same way as we do. They have three beams that interfere under 120 degrees to generate this lattice potential. And if you play with the polarization of these beams, you can also apply AB offsets in this lattice. Now, something that I've mentioned briefly is if you make this sublattice energy offset between A and B sides very large, then essentially the ground state is in the lower potential energy side, here B, and the excited band will be at all atoms in A, in sublattice A. And in this limit, if you make the tilt very large, you have essentially two flat bands that are separated roughly by delta AB. And this is what they use as a reference for their scheme. So this is what is shown here for the parameters they use. In their case, delta AB was around 11 kilohertz. And here you see the dispersion of the band, the lower band and the upper band, where if you look at the eigenstates, the quasi-spin that we had also for the SSH model for the lower band, this one is mostly on one sublattice, and this one is mostly on the other sublattice. So if you think about our pseudo-spin, they are at the poles of the sphere. And then the idea is to use this as a reference. So you first prepare your dressed eigenstates in a Fluquet scheme, and then you project back onto these bands. Okay, so this is how they start. This is done with fermionic potassium atoms. So they start in a flat band, which they denote as Kb, which means K is the quasi-momentum, and B is the B sublattice. So the pseudo-spin basically points up on our pseudo-Bloch sphere. And you can think about having such a Bloch sphere for each quasi-momentum. So it's really little spheres for each one, and all of them are pointing up to start with. Then they prepare the dressed band. So they turn on the modulation in order to prepare these dressed states. And they will be then a superposition of Ka and Kb because they get mixed by the, this is something I should mention, by the shaking. So in this case, the shaking frequency is near resonant with the band gap. So there's a small detuning, but it heavily mixes the two bands. That's why you can write the states that you then get in the dressed bands in the following form. Okay, it's a superposition between Ka and Kb and some phase angle phi. So it essentially rotates on your Bloch sphere. And now you project it back onto your flat bands, which means that this pseudo-spin now starts to process around the poles, which are like your effective magnetic field for your pseudo-spin. And then you can read out the dynamics of this pseudo-spin after time of flight. And this happens for each quasi-momentum. So you take snapshots of the quasi-momentum distribution after time of flight, which looks like this. And they really evaluated the oscillation for each pixel. So each pixel is some region of quasi-momentum. And then they get these oscillations, as you see here. And from these oscillations, you can then extract the projection, so the theta angle on your Bloch sphere, which is essentially this tilt here, and the oscillation frequency in order to extract. So the oscillation frequency is given by the band gap, nu k, that's the energy difference between the two bands, and then the phase of this oscillation is given by phi of the rotation of your spin. So you can evaluate this for each individual pixel. So you can reconstruct the eigenstates of your dressed band. So what you want to know, is this state. So now you know the angles theta and phi. So you know everything about your system because from these angles theta and phi you can compute the Berry connection, the Berry curvature, and everything else you want to know about the geometric properties of the band. And this is what you see here. So they extract the amplitude of the oscillation, which gives you theta, and the phase of the oscillation, which gives you phi, and then using that to compute the Berry curvature of the band. So here you get really, because you evaluate each individual pixel, which you have in your CCD chip, you get a local map of the Berry curvature of the band. I think this is a really cool measurement. And here, if you want to know the Cherndorf of the band, you just need to sum up all of these values. So here the blue region would be negative Berry curvature, the red region positive Berry curvature. So if you integrate all of these values, you get, for this specific case, a Chern number equal to 0. But you can apply that also to Chern bands with non-zero Chern number. There's not a lot of enthusiasm. Yeah.
Why isn't it 0 at the center? I thought the curvature
Yeah.
near came along.
Good point. So that's because of the technique that they use in order to engineer the bands. So what I have told you is these Dirac points that we have in the normal hexagonal lattice and then opening up a gap, and I explained you how the Berry curvature changes if you do that. Now, this is done for off-resonant shaking. Here they use some mixture in between the resonant shaking protocol that we use in the square lattice and the off-resonant shaking protocol by doing a near resonant shaking, and then moves around the high symmetry points. So here actually the K and K prime points or like where we have concentrated Berry curvature are in the center and on these three edges. So it's moved around. The region of Berry curvature are not where they normally would be in a hexagonal lattice. But this is just due to the fact that they start out with these flat bands with a very large energy offset between A and B sides. And then they apply a shaking which is near resonant with this gap. That's why the dispersion relation that you get looks different.
So the whole band structure has been shifted?
No, it's not really a shift of the band structure. It's really a deformation, rather. I think you can see it. That's something that I will tell you later. But you can play around with these band structures in the Floquet framework. So if you think about a band structure like this, that's the two lowest bands that we typically deal with. But now if you have a periodically driven system, then this is your quasi-energy axis. So you actually have another copy here. And you can create mixings between these two bands, which would then also create Berry curvature at a gamma point, for example, at the center of the Brillouin zone. So that's always the picture I have in mind. So if there's a band touching point, let's say at gamma, it will be the source of Berry flux at the gamma point. If you only play around with the K and K prime points and open and close gaps here, it will remain concentrated here. And then you can spread it out by making the band more flat. But if you introduce mixing here, then it would create Berry curvature at the gamma point. I think there was one more question. No? Okay, that's fine. Okay. So yeah, I think this is really nice and also shows the degree of control we now have achieved in these periodically driven systems, which allows us to directly map out these geometric properties. Now, a few slides on topology in reduced dimensions, basically because Thierry also highlighted it a few times. So I just want to briefly mention two examples of how we can study topology, also quantum Hall systems in reduced dimensions. Okay, so there's something screwed up. So here, now there's a lot of stuff on the slide, so let me walk you through. The idea is to generate a topological charge pump. So now, reset, we only have a 1D lattice, no artificial gauge field whatsoever. It's for now just a static superlattice potential, the SSH model, okay, our favorite 1D model. Where now, on top of that, we slowly vary the shape of the potential in time. Not applying a force, we really play with the lattice parameters. And the idea of a topological Thouless pump is that, again, if we perform some adiabatic cyclic evolution in an abstract parameter space, which I will tell you in a second what it is, we can realize a quantized charge pump. That means, in our case, if we vary one of these two lattices, so the superlattice is generated by superimposing two standing waves. So we have one lattice and another one at twice their periodicity. We can move one with respect to the other, which means that we will vary the shape of the superlattice potential from something that is symmetric, as shown here, to something that is tilted. At some point it will be symmetric again, and then it will be tilted again. And if we think about the SSH model or the Rice-Mealy model, it means that we are changing the dimerization of the tunnel coupling as a function of time, and we change the AB offset as a function of time. So if we just move one lattice with respect to the other, we basically trace out such a loop in parameter space where we have the dimerization and the sublattice energy offset. And I mentioned that in the center of this plot, we have the degeneracy point, because that's the point where both tunnel couplings are equal and delta is equal to 0. So in this case, the two bands touch, and we have something like this. And the idea is that now in this abstract parameter space, I can also compute geometric quantities. I can compute in this delta and J parameter space a Berry curvature now as a function of phi and quasi-momentum in the 1D lattice. So phi, in this case, is a single parameter, as you wish, time, that characterizes how the potential changes. So in our case, it's phi of t, but since we look at geometric quantities, we just look at the parameter phi. So we get a Berry curvature, as it is shown here, in our parameter space qx of the 1D lattice, and phi, this parameter that we vary adiabatically as a function of time. And if we integrate it, it means we integrate the whole Brillouin zone, because this evolution is cyclic, meaning that if I perform one loop, I will end up again with the symmetric double-well Hamiltonian, the symmetric SSH model. So this is one periodicity of the pump. So now again, I have a 2D parameter space, which now is not qx, qy, but qx and this parameter phi. So I can integrate this. It's a closed manifold, which again counts the number of monopoles in the sphere. And in this case, we have one degeneracy point at the center of our parameter space, which is the source of the non-trivial property. So if we integrate over the Berry curvature, we find a Chern number that is equal to 1. And the result of that is that the topological transport that we induce by doing this adiabatic motion is proportional to the Chern number that characterizes the pump. So now we have a Chern number that is associated with the pump cycle. And it could be 1, but it could be also -1, for example, which is maybe a bit more counterintuitive, because plus or minus 1 gives you the direction with respect to the direction where you vary the potential. So if you move your potential in this direction and your Chern number is equal to 1, the atoms would be also displaced in the same direction. If your Chern number is -1, they would move in the opposite direction, although you move your lattice in that direction. And this is what is schematically illustrated here. So you have like a classical ball would always remain in the minima of your lattice potential. But now for the atoms, they are here shown in the 1D orbitals of the respective superlattice or double well that participates in this dynamics. It will start to move. And well, once you understand how the pump works, you may say that's a little bit trivial, because what happens is that, okay, if we are in the symmetric double well, then the 1D orbital of the symmetric double well is just a symmetric superposition between left and right. So that's your initial starting point. And now as you start to tilt the double well, it will just move over, it will hop over to the neighboring site. And then it will continue doing so. So it moves over to the neighboring site. That's also where the Berry curvature is largest. So it signals that there's some current induced. And then it will again tunnel to the neighboring double well. So this is basically following the 1D orbital computed for the double well potential. And then this is what you see. So this is the quantized transport that you can measure by performing this adiabatic change of the lattice potential. So you see these steps, which, so that's a bit counterintuitive. So it's, in this case, actually not the steps that are quantized, but the points in between. So that's a little bit tricky to see, but that's our starting point, 0, and one pump cycle ends here. So it's actually at this position here, which is very hard to measure. So if you change the way you vary your lattice potential, then all of this can be deformed, but these points, they are pinned, they are fixed. So that's what fixes the topological transport in our case. And then you can also do it for the higher lying band. You can do it for the second band, which, as we know, has a Chern number with the opposite sign. And then you start to see that they move to the opposite direction. Now, this is a little bit more challenging to do, just because it's harder to prepare the atoms into the excited band. But you see that instead of moving in the same direction as the lattice, they move in the opposite direction. And something that I don't have time to go through, but you can see this topological pump. I already anticipated it a little bit, that has these two parameters, kx and phi, as a 1D dynamical version of a 2D quantum Hall effect. So there's actually a mapping between the two that you can do, where you map phi on qy, as you would have in a 2D system. And so in this 2D system, you also need a flux, right? We had our flux phi per plaquette. And this flux phi is played here by the ratio of the two lattice constants. So here by the lattice constant of the short lattice and the long lattice. If you vary that and you go to different values, here it's a ratio of 2, but you could choose a different ratio, let's say 4. Then you can map this to a, plus some corrections, to a 2D quantum Hall system. So 1/2 would mean a flux of pi, and 1/4 would mean a flux of pi over 2. So it's like a dynamical version of the 2D problem. And you can also generalize that to spins. So you can induce spin currents, which go in opposite directions. But moreover, since you can visualize this 1D pump as a reduced or dynamical version of a 2D quantum Hall effect, you can also go to higher dimensions. You can apply the same concept and study 4D quantum Hall systems in a 2D topological pump. So this is what has been done in this paper here, where you see now instead of having a 1D superlattice, there's also a superlattice along the perpendicular direction. Okay, questions? I see you're getting tired. Okay. Now the flux ladders, something that has been shown very briefly yesterday. We can also do some physics with these artificial gauge fields. And one of the easiest geometries for us to handle experimentally, but also theoretically, are quasi-1D systems, or so-called ladders, which we can realize with our double wells. So we chop off the coupling between neighboring ladders, such that dynamics is only happening within one of these strips. And that's like the smallest geometry that you can think of, which is still pierced by a magnetic flux, where you can study effects of orbital magnetism. So here we have complex tunneling along the red bonds and just normal hopping perpendicular to that. And now you can study the ground state of this flux ladder as a function of the parameters of the model. So as a function of J and K, which are the two tunnel couplings, and as a function of the flux that is piercing the unit cell, which is something that we did not vary in that experiment, but you could also vary the flux associated with the unit cell. And so if you look at the ground state in this model, non-interacting, so still single particle physics, it turns out to be very interesting because you can compute chiral current as a function of the artificial field that you apply. So a chiral current would mean the current going up here on one leg and going down here on the other leg of the ladder. That's our chiral current. So you can compute that, and then you find a diagram like this, which maybe reminds you of another system that you know of, like a conventional type 2 superconductor. So indeed, for low values of the flux, you see that the chiral current increases with the applied field up to some critical value. And for a type 2 superconductor, that would mean that in this regime we have full screening of the external field. And at some point when you hit a critical value, the field starts to penetrate and you have this vortex lattice forming. And now if you plot the chiral current for our system, you see something very similar. So in this so-called Meissner phase, you see a nice chiral current where the current goes in one direction on one leg and the opposite direction on the other leg. It's uniform. But then in this region, in the vortex lattice phase, they start to break up and form the small vortices in the current pattern. So you see here one and another one here. And depending on the parameters, you can also have more of these vortices. So that's a vortex lattice on the flux ladder. And we can actually measure these chiral currents in the experiment by chopping again our ladder into pieces. So essentially this current operator can be measured by converting the current into oscillations in a double well. So the idea is if you have a current along a bond, and then you isolate it, so you chop it off here and project it onto a double well, this will be converted into particle oscillations between the two sides of the double well. So this you can derive. There's a relation between the two. And what we were able to do is independently read out the current on this left leg or left bond and the current on the right bond, where you see nice out-of-phase oscillations. So I didn't plot the data here, but you can look them up in this paper. It's a nice example of how these completely different systems, which are charge-neutral bosons, can somehow mimic effects or analog effects as you would have in a completely different system, which is a type 2 superconductor. Okay. Yeah.
I'm doing that, and I want to add dissipation. Which type of losses do you have in these things?
So, but you are, what type of system are you looking at exactly? So the analog system, our system, or
Non-analog, exactly. Non-interacting pattern.
yes, okay. So it's non-interacting.
Which type of losses do you have in these setups?
Well, okay. So maybe we should discuss about that longer to discuss the details, but. Yeah, it's a bit tricky to say that in terms of like a term in the Hamiltonian that you could directly apply, because this is single particle physics, so particle loss will not do much, I think, unless it destroys. Yeah, so we should discuss. Huh? Okay, so that's one example that I wanted to show you, where we use this artificial gauge field scheme in order to study also some physics. Other questions? Yeah.
Are there some compact analogs, like these strips?
Sorry, say it again.
This ladder, I mean,
Mm.
this ladder physics in Condens matter. I mean, here is very specific, like really ladder, and are they Condens matter?
Condensed matter analogs of this in like low dimensions and
Because you mentioned
small
like
systems.
conductors, which usually is like extended.
Yeah. I don't know. I think it's an active field of research, but I'm not sure if there's a solid state experiment that is in a similar regime. I'm not sure. Okay. Yeah.
One thing which kind of always bothers me with ladders is that in a sense the edge of the system is also the bulk of the system.
Yes.
Because it's not anything in the middle.
Yes.
So, is there something about which is special or which you have to be careful about?
Yes, so it's actually remarkable that the main properties of these phases, they remain. So you can do a diagonalization study of how the spectrum changes if you add more and more legs, like if you start to have a bulk in the center. It nicely extends, so you can play this game and extend it to a full 2D system. And these chiral currents that are here in the Meissner phase, they actually relate to the edge modes in a 2D quantum Hall, like in a fully fledged 2D quantum Hall system. Yeah. Yeah.
I know that in some of these ladder systems, you also, I mean, if the system isn't too large, you can change dramatically if you change the edges of the system.
So here again, we have a harmonic trap, so we have this smooth profile. We don't really have an edge. So we didn't look at this, yeah. All right. So now, one last topic. That is, can we go beyond just mimicking what we already have in condensed matter? Can we maybe use all these techniques and do something new? And so the spirit of everything that I told you so far is trying to emulate what we see in quantum Hall physics in solid state, which is nice. And I still like this topic, and we want to go to the interacting regime. But now we have this periodic driving, so maybe we can do more. And this goes back to what I started sketching here, because now you can play not only with your static band structure, open up gaps, and so on, but you can start to play with the Floquet spectrum itself. So if you have two bands here and another copy up here in your quasi-energy spectrum, so this is h bar omega, you can ask the question, what happens if you leave this high-frequency driving regime, where we send this to infinity? Now we bring it closer, which means that we can induce mixing between different Fouquet zones. So we can really bring this gap to 0 and mix these bands. And this leads to new topological phases, which don't have any static counterpart or any static analog. And as you can see here in the spectrum, in particular what you can have is that there are edge modes that enter this Fouquet-Brillouin zone from below, which you cannot have in a static system because there's a true notion of a lowest energy band. You cannot just have an edge band, an edge mode coming from below. In the Fouquet spectrum, you can have that. So there's essentially a winding of this edge mode around the Fouquet zone, the Fouquet-Brillouin zone. So in this particular example that is plotted up here, you can have edge modes although the Chern numbers of the bands are 0. So the relation is that the Chern number of the band is the number of edge modes leaving the band from the top minus the one entering from below. Okay, so here we have one above and one below the band, so the Chern number of the band in the middle is equal to 0. Nonetheless, there seems to be something topologically non-trivial. And there are ideas, I think, well, there's not so much yet on this topic, but in principle, you may imagine that this system may even be more robust as compared to a conventional quantum Hall system, because the winding of the edge modes should persist even if all the bulk states of these two bands are completely localized, something that will not happen in a conventional quantum Hall system. But this is something we are interested in studying, and I think there's not a lot on this topic yet. Okay, so what is that actually? So I can explain you in a toy example why there's something non-trivial happening if you leave the high frequency limit. So this is a very fine-tuned example where we have a 4-step modulation protocol where atoms only tunnel along the colored bonds for a quarter of the period. And it's very fine-tuned in a sense that if you start with a particle here on the black dot, the time it takes to tunnel over to the neighboring site is exactly the quarter period of the modulation protocol that was chosen here. So if you were to start with an atom on this black site and go through these 4 steps, it comes back to where it started. So it has completed one cycle, and essentially the time evolution operator for one period of the drive is the identity. Nothing happened. So, well, you would say, Mea, the Fouquet Hamiltonian is probably trivial. There's nothing very much interesting that happens. Now, if you compute the spectrum, you find 2 flat bands with trivial topology, no Chern number. But you can ask yourself what happens if you put edges. So if you look at a finite system, and you will see that a wave packet prepared on the upper edge, it will travel to the left, and a wave packet prepared on the lower edge will travel to the right. So there still seems to be something non-trivial, and this is actually are these edge modes shown in red and green here in the spectrum. So there are edge modes, although if you just do this naive analysis of the Fouquet Hamiltonian and compute the topological properties, you wouldn't see that there's anything non-trivial happening. And in order to see that there is something non-trivial, you actually have to take into account what happens during one period of the drive. So this is, in other words, just saying that we leave this high frequency limit. We cannot just assume that everything is described by the 2 bands of our Fouquet Hamiltonian. We have to take into account what happens within one modulation period, or in other words, we need higher orders of this Fouquet expansion that we have seen previously, and really look what the micromotion also does at times within one driving period. And then one can compute new topological quantities that characterize these bands. And this has been realized in photonics, so there it's relatively easy to do. You have seen these coupled waveguide arrays. Or maybe I have a picture. Yeah. So there are these coupled waveguide arrays. So if you bring them closer to each other, it means that there's tunnel coupling. And if you bring them further away, there's no tunnel coupling. So you can write these waveguides in a way that implement this stepwise modulated protocol. So it is a slightly different version. It's a little bit more complicated. It has additional parameters, but the idea is very similar to what I've just shown you. And then you can perform similar measurements as Jacopo explained. So you can launch photons into one waveguide and see how they propagate around the edge. And you see also the topological robustness. So if you put defects into the array, the photons will travel around it. And if you launch photons into the bulk, they will perform a cyclic evolution. So they're essentially localized. If you would probe the system at stroboscopic times, they are essentially always in exactly the same waveguide. So yeah, it would be nice to do something like that with atoms. And of course also study many-body physics, because there are some very interesting band structures that emerge. Okay, so just very briefly, what we need are new topological invariants. So we need to compute winding numbers that directly tell us what is the number of edge modes in a specific gap. So for this two-band model, we now need two topological invariants to characterize it. Previously, we were happy with just one Chern number, because we know the sum of the two is equal to 0. Now we need two independent ones, which are these winding numbers that we can compute from the time evolution operator. Okay, so first of all, how do we do that, and how can we measure these topological invariants? So in all the measurements that I will show you, or maybe I will skip that and just show you how it works, because I don't have enough time. So let me skip to, oh, actually this touch bar is quite nice of the new Mac. I've never used it before. Okay, so what we do, no, it doesn't work. Or maybe I'm just too stupid. What we do is implement a hexagonal lattice that we modulate, similar to the stepwise modulated square lattice. That means we modulate this 3 different tunnel couplings. So we have T1, T2, and T3, and we can vary their relative strength. Okay, so that's a plot of the potential as a function of time at 3 different instances. And the red one is where we increase the tunnel coupling and make it larger as compared to the other ones. And luckily, this is very easy to do, because we have these 3 beams that generate the hexagonal lattice. And if we vary the intensity of one of them, it imbalances the potential and increases the coupling along one specific direction. So all we need to do is actually apply a sinusoidal modulation to all 3 beams out of phase, and this will directly implement this modulation scheme. Okay, so this is very easy to do. And now if you look at the phase diagram, you see the following different phases. So in the high frequency driving limit, since it's also another variant of a circular shaking, we open up a gap at the Dirac cones and we get to the Haldane phase. So here's a spectrum computed for an infinite strip. You see the 2 bands, you see the edge modes around 0 energy, and the Chern number, if you compute it for the 2 bands, is plus and minus 1. Now let's move along this line. Now we do exactly that. So we move the copies closer into each other. So we get a band touching point here, which actually means we create an edge mode between Fouquet zones, but without actually removing the one around 0 energy. So this is what you see here. We get a gap closing point as we decrease the modulation frequency. And now we have an edge mode up here. We still have the edge mode here. And if you compute the Chern number of the 2 bands, it's equal to 0. And then there are a series of other phase transitions if you move to smaller and smaller frequencies, because essentially you move all of these copies closer and closer together. Oh, sorry. So there's another Haldane type phase where you have an edge mode only between Fouquet zones, and now no edge mode around 0 energy, and also Chern numbers of plus and minus 1. Okay, so what can I tell you in the end? So this is something that we measured, and actually you can probe these gap closing points again using this. So I showed that because I had a question yesterday about that. You can again probe the energy gap as a function of your modulation parameters using this interferometry technique that I shown you before. And what we did, again, was to have this coherent superposition between the upper and lower band. And then we have this time evolution according to the gap frequency. But now we are in a Fouquet system. So we can either measure this frequency or we can measure this frequency. But remember that what we do here is we probe the system at stroboscopic times, integer multiples of the driving frequency. So the largest frequency that we are able to extract from this time interferometry sequence is omega half. That's the largest frequency that we can measure. and the sum of the two is always equal to omega. So essentially what that means is that we will always measure the smaller one of the two frequencies. And so if we start in the high frequency limit where this copy is far away, we will probe the typical two bands that we worked with the whole time. But now if we move the copies closer together, there's a point in the gap measurement where we reach h bar omega half. So this is the high frequency limit. Here we measure exactly h bar omega half. Then it decreases again. And that's the point where we start to probe the gap between Fouquet zones. So actually from this diagram, we can immediately read off what the gap is and where it closes. So over here is the high frequency limit. Here it changes. So here we see a gap closing point between Fouquet zones. Then it increases again. We have another cusp. So here we actually start to measure again the gap around zero energy. So we see that there's another gap closing point where the gap around zero energy closes. And so if you go back to the spectra, that's exactly what happens along this line. So first we have a gap closing point here. It generates an edge mode. Along this line, we have a gap closing point around zero energy, which removes the edge mode that was previously at zero energy. And so we can see all of that with our energy gap measurements. And we also can probe locally what happens to the Berry curvature as we move across the phase transitions. So these gap closing points that happen here, you can associate topological charges to these gap closing points, which tell you how locally the Berry curvature changes as you go across the topological phase transition. And this we can map out by performing these local Hall deflection measurements. So now if there's Berry curvature concentrated here, you can take a cloud, you move it across this region in the dispersion relation and measure the associated Hall deflection. So this allows you to extract a local Berry flux even from these transport measurements that I've shown you before. Okay, so we did that in order to characterize this interesting phase diagram. So in the end, what you get is something like this. You see a local Hall deflection measurement, and you see in the upper plots how the Berry curvature changes across the phase transition points. So this is one jump across the phase transition. Gap closing happens at gamma, which is here in the center. And what you see is that there's a positive Berry flux developing just before the phase transition, which then flips sign just after the phase transition. And this is how you can characterize also the topology of these band touching points. And something similar happens for the second transition as well. Okay, so with this, I'm done. Let me just have two more sentences. I know I'm already over time, but just to tell you what people are thinking about doing now. You could include back action. So we have engineered artificial fields, but if our atoms move around, they don't generate any field. So if you want to have something like that, you can play with density-dependent fields such that if atoms move around, they actually affect the gauge field that you realize with your laser-assisted tunneling techniques. And you can even generalize that further and go in the direction of lattice gauge theories, where you now really have like fields that have their own degrees of freedom, and you couple them to matter and you play around with those. And we have performed one experiment on that in C2. But to close, what our main line of research is also at the moment to study interacting topological phases of matter. So you have seen symmetry-protected phases in the SSH model very briefly. And there are also higher order symmetry-protected phases in 2D that we can study with interacting bosons. And then our ultimate holy grail, as was already mentioned for photonic systems, is studying fractional churn insulating states, which we are also planning to continue. And something that I find also very interesting is to directly study the interplay between topology and disorder. Okay, so then I just flash the last slide with some review papers if you want to read more details about some specific topics. Okay, thanks a lot. Yeah.
About the nature of these edge states that you have in the higher bands, or between the higher bands, do they talk to each other? Do they have some scattering? Are they protected among each other because they share the same edge? Right.
No, they don't talk to each other. They are protected. Yeah. Other questions? If not, yeah. Okay.
Is there any possibility to extend this one day to look at like three-dimensional topological insiders?
Sorry.
The three-dimensional topological insiders?
Oh, yeah, that's a good question. It's a bit harder to do. So I think in principle, yes. So there have been also schemes to realize while systems, for example. It's a trade-off, I would say. So there are schemes to do that, but you lose a little bit of control. So what we like about our 2D systems is that we can then also build microscopes, we can see individual atoms, we can manipulate individual atoms, so this gives us a lot of control and flexibility. For 3D, that would be much more difficult to do, and also to study the properties of this 3D system, but in principle it can be done, yeah. Okay. So then I let you take some coffee, and if you have more questions, we can also talk later. Thank you.